Okay. I'm waiting for my chime. All right, there it is, you guys. Okay, so all I did here is I just reformatted the notes. I had too many things on one page of paper, so I've since reformatted them. You'll be looking at this version of the notes when you're taking these notes. Excuse me. So I just finished answering question H, okay? And that talked about where it has a relative minimum, find where those points are. And I justified it with the sign diagram and found the coordinates of those, although my pieces of notes are all over the place. Okay, this one I just recopied the graph and I redefined the function here so we can, as I'm answering these, I can be looking at them at the same time, okay? Okay, so look at question I. It says, specify the coordinates of all points on the interval where G has a point of inflection, okay? An appropriately labeled sign diagram will help to justify your work. So remember, we call this integral, when this is a constant and these match, this integral, we're going to call that a capital F of t, the derivative of, I'm sorry, the antiderivative of lowercase f of t. And so basically, we are establishing that g of x is an antiderivative of f of x, okay? And I know it, whoops, I really should call this f of x in this case context because that's g of x. So there we are. We replace all of the x's, all of the t's with x's when we evaluate. Okay, so we're using g as basically the integral of f. So at that point, if we take the first derivative of g of x, that's the first derivative of capital F of x, which is just by definition f of x, like so. Okay, and so this problem is asking us for the second derivative of g, which is equal to the first derivative of f. And so basically what we need to do is make a sign diagram of g double prime of x, which is equal to f prime of x. And so we need to evaluate this function here, its derivative. Okay, well, that's not too bad because we know that its derivative is positive here. We know its derivative is 0 there. We know its derivative is negative here and negative here, and it is positive here. Okay, and so we're just going to make a sign diagram here of what we see. -6 is one of our endpoints. Okay, I'm off the paper as always. Okay, gosh, no matter how hard I try, I can never squeeze everything in the same spot. And at the other end point, we have a +6, like so. Okay, all right, and then we now look at, well, where does this derivative break? Well, we have a break here between -6 and -3. Okay, so on my sign diagram, I'm going to make a break at -3. And then my next break here is at -1, okay? And then the next break is at 1, okay? And then the next break is at 3. And then last, everything ends at 6 there, okay? Now, something I need to be careful about here is the second derivative. When I make a sign diagram like this, that usually means the second derivative is 0 in these spots, and I need to be really careful about that. At -6, that's an endpoint. The second derivative, the slope of this is positive, okay? And so I'd rather not make that into a little dash. That usually means negative. So from this point to here, it's positive, okay? All right, and then at -3, notice the derivative of f doesn't exist. It goes from positive to a derivative of 0. Okay, so right here, it switches to a 0, okay? But I need to be careful there. It really isn't 0 there. That derivative does not exist at -3. The second derivative does not exist at -3, okay? All right, and then at -1, right here, we have the exact same issue. The slope of the derivative of f goes from 0 to negative. And so I put a negative here on my chart, but at -1, technically, the second derivative does not exist, okay? Like so. Okay, and then it's negative until I get to 1, and then it's still negative after that. Between 1 and 3, the derivative is still negative, okay? And once again, the second derivative does not exist at 1. So this little mark here, DNE, the second derivative technically doesn't exist at 1. Okay, and then same problem when I get to 3. When x is 3, the second derivative changes from negative to positive. Okay, so on my sign diagram, I'd put a positive here, but at this spot, it technically does not exist. Okay, and at 6, the second derivative is positive as well, and so it exists there. Approaching from the left side, it's positive, like so. And there I have it, okay? Sometimes I think a better way of managing this is to make it clear that you're graphing, you know, g double prime of x, which is f prime of x. I think sometimes it might make more sense to do like this. Instead of trying to say that the derivative is 0 at those spots, I think it's a little easier if I do like this. From -6 to +6, these are the endpoints. This is an endpoint, okay? And then the second derivative is positive, 0, negative, negative, positive. And then I'm kind of avoiding the whole issue at -3, at -1, at 1 and 3. The second derivative does not exist, okay? So I think this might be an easier thing to understand than up here. As long as you're justifying your work, either format is fine. I would just be very cautious about leaving this as like a ticky mark there, because that signifies that the second derivative is 0 there, and the second derivative doesn't exist there. So this is another way to get around that issue, okay? All right, once you've successfully made a graph, a sign diagram of the second derivative of a function, all you look for is where does it switch concavity. It has to go from a negative to a positive, or a positive to a 0. Okay, I'm sorry, no, it has to go from a negative to a positive, or a positive to a negative. That's all there is. Here, it doesn't change sign. It goes from positive to neutral. Here, it doesn't switch sign because it goes from neutral to negative. Here, it doesn't switch sign because it goes from negative to negative. Here, it does switch sign. It goes from negative to positive. And so we end up with, we have a point of inflection at x equals 3, and at x equals 3, and then of course g of 3. Okay. Now a couple of things to consider. In order to have a point of inflection, you technically need to have a single tangent line. Okay. And so let's look at 3 when x is 3. Let's take a look at this. At 3, f of x is equal to -3. F of 3 equals -3. According to this right here, it's defined there. This is by definition g prime of 3, as we've talked about before. Okay, that's the derivative of g. It's defined. It's just -3 there. We don't have a discontinuity here, so we're perfectly fine there in declaring, yes, indeed, there's a single tangent line on the graph of g there, okay? So now it's just a question of, this question asked us, it said, determine the coordinates of all points on this interval where g has a point of inflection. And so all we need to do now is evaluate g of 3, okay? Fortunately for us, I think we did that earlier, maybe not. I thought we did. No, I suppose we did not evaluate g of 3. Okay, so we need to evaluate g of 3. So it's just a matter of applying the definition of this. Basically, back up here, when we want g of 3, we would simply plug in -3 to 3 of f of t dt. Okay. And let's see. So we want to integrate from -3 to +3. We want to integrate that. Okay. So what we want to do, I think the best thing to do is to break this down into 2 pieces. We've already evaluated this integral multiple times. The integral from -3 to 0 of f of t dt plus, and then the integral from 0 to 3 of f of t dt, like so. Okay, so this derivative we already evaluated. That one we already did. The integral from -3 to 0, we evaluated that earlier. Let's see, we did it right here. The integral from, why can't I find it? From -3 to 0, we've already evaluated that is equal to 5. Okay, so that equals 5. And then we need to add in this area here. We were talking about that earlier. This triangle here, that would be a negative contribution to area, -1/2 of its base times its height 2. And then we need to subtract the area of this trapezoid, which is you average the bases. So this base is 2, and this base is 3. So add those together, that's 5. So we take half of 5. That's the average of the bases multiplied by the height, which would be 2, like so. Okay. And so so this is 5. And then this integral here from 0 to 3 is equal to these pieces in here. Okay. So we ended with 5. That's minus 1. And then minus 5 again. And so we end up with, these go out as negative 1. So we end up with g of 3 is equal to negative 1. Okay. So we have a point of inflection at x equals 3. And g of 3 we evaluated was equal to negative 1. So we have a point of inflection at 3, negative 1, like so. Okay. All righty. Okay, next one. Calculate the average value of this function on the interval from 1 to 6. Okay. And so to do this, we can memorize a formula. This is A and this is B. Generally speaking, if you just look up the textbook formula, it's going to tell you to integrate the function, get the total area. That would be going from 1 to 6. Well, let me write the formula down. The integral from A to B of f of t dt. You could say f of x dx. And then that's the total area. And then we have to divide that by the width. Okay. And so instead of dividing by b minus a, we multiply that by 1 over b minus a, like so. This is one way of handling it. Okay. And so we have b minus a, that would be 5. So we want 1/5 of the integral from 1 to 6 of this function f of t dt. Okay. And so we basically need to figure out, well, what's the area going from 1 to 6? Okay. Well, we just need to add these pieces together. Okay. These are negative contributions of area because they're underneath. And so the integral from 1 to 6 of f of t dt, I'm just going to break it into pieces. We've done this before. The area of this trapezoid here, we said earlier, the area of a trapezoid is the average of the bases. So if you add the bases together, the parallel sides, 2 and 3, you get 5. So that would be 5 halves. That's the average of the bases multiplied by its height between the bases, 2. Okay. And I want to make sure that I make it negative since it's underneath, like so. Okay. And then the next piece is just a triangle. Base and height are both 3. So minus 1/2 of 3 times 3, like so. So this component here would be negative 5 minus 9 halves, or negative 10 halves minus 9 halves, which would be negative 19 halves. So that's this component here. That area there from here to here, from 1 to 6, is negative 19 halves. And then remember, the average value of the function, the average value of this function is equal to 1/5 of negative 19 halves, or negative 19 tenths. Okay, so the average value of this function is negative 1.9. Okay, so if you look at this function and you write down every possible value of this function, you know, at every value of x, okay, what's the average of all of those values? You'd end up, if you make an infinite number of them and you make each contribution infinitesimally small, the average of all of those different pieces would be negative 1.9, or about negative 2. Okay, and that's just around right here is the average value of this function. That actually seems reasonable. Okay. All right, and then fun times, look at K. Suppose we define H to be this funny function based on F with all of these crazy arguments and so on, okay? Very typical BC Calc test question. You'll see this type all the time. And you simply follow the rules, okay? That's all you do. You just take the derivative and you You take it where the algebra and the calculus take you, okay? So they want h prime of 2. And so the first thing I need to do is ask the question, well, what is h prime of x equal to? Well, one step at a time. By definition, the derivative of a constant is 0. Okay, then I have 7. So I can always take the constant out, and I simply multiply it by, now I just have to evaluate the derivative of that. Well, by definition, you do the derivative. The chain rule says take the derivative of the mama. So that would be f prime of x squared minus 9. Leave the baby alone. Okay, take the derivative of the mama, f prime of x squared minus 9. Leave the baby alone, but then multiply that by the derivative of the baby. Well, what's the derivative of the baby? Well, that would be 2x, like so. Okay, and a constant is 0. And since I ran out of room anyway, I'm not going to write that because I'd just be writing a plus 0. So h prime of x must be equal to 7 times f prime of x squared minus 9 times 2x, like so. Okay, and I don't know what that means, but I just follow the algebra. I'll take it where it takes me, okay? So they want h prime of 2. Well, that would equal 7 times f prime of 2 squared minus 9 times 2 times 2. Just like so. Okay, I'm just doing the algebra. I'm replacing x with a 2. Everywhere I see an x, I put a 2. So I end up with, let's see, 2 times 2 is 4 times 7 is 28 times f prime of 4 minus 9, negative 5. So now I have to figure out, well, what's f prime of negative 5? Well, that's by definition the derivative of f at negative 5. And we are talking about here at negative 1, 2, 3, 4, 5. So what we need is the derivative there. And we talked about that earlier. I did all kinds of complicated calculations there of that. And basically, the slope there is 2 to 1. Rise 2, run 1. So we know that that's 2. So we end up with 28 times 2, which equals positive 56, like so. So h prime of 2 is 56, like so. Okay? Alrighty, guys. Those notes are grueling. There is a whole lot there. There are tons and tons and tons of steps. And if you just discipline yourself to follow the rules of calculus and follow the rules of algebra, you are going to be absolutely fine. Okay? Alrighty, guys. Hope everything's well. All right. Take care, you guys. Bye-bye.